Okay. So, good morning, everyone. My name is Geoffrey Biggs. I'm from the National Institute of Advanced Industrial Science and Technology, based in Tsukuba. And I'm going to be talking about the RT-Middleware project, or more specifically, the open source parts of it. So, RT-Middleware is a Japanese project to develop a complete development and runtime environment for robotics, so that you can develop your robot in this environment and then run it using tools that are also related. It's an entire platform, so there's a middleware and there's a variety of tools involved. And the idea of this is that you have a complete end-to-end chain of tools that you can follow through the entire process, from development to deployment. So one of the core parts of it is a middleware for distributed intelligent systems. This is a component-based middleware with a standardized component model. And by using a standard for the component model, it enables us to have many software makers develop tools that can work with the same middleware just by complying with the standard, which is quite important for creating an open and flexible tool chain, particularly one where you have alternatives at every step of the process to create a market, an economic market. Let's see. So I'll give you a bit of a history of the project. This project's been going for quite a long time now. It started right back in 2002 with a Neto project for RT-Middleware. This Neto project has continued on and followed on to new Neto projects over the years. So we're up to currently in the third project, which ends at the end of this financial year. No doubt there'll be something following on from that to continue on the work. Within this project, the RT-Middleware itself has had quite a few releases over the years. The first test version was way back in 2003, and we're currently on version 1.0, although actually we're in beta release of 1.1 at the moment. We expect that to be released sometime this year. So over the years it's changed a little bit, but the core principles of the middleware have stayed the same. It's always been component driven, with various specific features that are oriented towards developers and system integrators. In parallel of this, we've also seen some standardization efforts beginning in about 2005-2006 at the Object Management Group, where the component model of RTM has been standardized. That's the RT component model. That was actually initially submitted back in 2005 and 2006, and the 1.0 standard was published in 2008. So OpenRTM itself is the middleware at the core of the platform, and this is, as I mentioned, a component-based middleware. So this is an example of a component network for a very simple path-following robot. So the idea is that you have these green modules. These are the components, and you have connections between them, which are the data flows or the service requests and so on. So the component model itself is what defines the life cycle of those components, and each component has a state machine within the component model. So there's two levels of state machine. There's whether the component is alive or stopped or running, and within that running state it can also be inactive, active, or in error. And this allows us to externally manage the life cycle of a component from our tool chain, which gives us great flexibility in terms of deployment of components and introspection at runtime, finding errors and debugging and so on. One of the important features of the component model is what's known as execution context. So this is basically an execution container concept. You'll find this in many other middlewares, in professional grade middlewares such as, I think, Java Enterprise Java Beans, for example, has it. And the idea is that you separate execution control from implementation, so that the system integrator is the one who can control how components execute instead of the component designer. And this gives a lot of flexibility when designing the systems themselves, because you can decide how you want your path planner, for example, or your sensor components to execute, how fast, what rate, whether they need to be real-time or not. And you can do that independently of whoever developed the component. And this gives a lot of flexibility to the system. OpenRTM itself provides many commonly used execution contexts. We have a periodic execution context, which is probably the most commonly used. We also have real-time versions of that. There's a composite execution context. Third parties also provide their own execution context. For example, the OpenHRP tool, which is a simulator, provides a synchronized execution context, so that you can synchronize the execution of your components to the simulation's time step. So if your simulation speeds up or slows down, so does the execution of your components. Another aspect of the component model is ports. This is quite an important part of the RTC standard, because This is how we separate out the implementation of the standard, the interfaces of the standard, from how components actually communicate. So within the RTC standard, a port is just a point of communication, and that separates out the introspection parts, the connection methods, from the actual communication method itself. So for example, we can have several different types of communication within the same component based on the port type. And so this allows us great flexibility, and again, it separates out what the system integrator can do from what the component designer has to do. OpenRTM provides several transports for its ports. By default, we have the Corba-based data flow and remote procedure call ports, but also along with that we have a TCP data flow port, which gives you a basic TCP connection, and also we've recently implemented the DDS, Data Distribution Service port, and this DDS is a complement to the Corba standard, which allows for data-oriented middleware development. And so that's a very fast, very efficient middleware, and we've recently implemented a port to use that, giving us about 20% speed up over using Corba by itself. So I mentioned that the component model in OpenRTM has been standardized. So this is the Robot Technology Component Specification. It's at the Object Management Group. They do a lot of standards for object-oriented systems. For example, Corba is one of their standards, and so is UML, SysML, and DDS, all OMG standards. This standard is quite specifically defines only the external interfaces for introspection and control of RT components, execution contexts, and ports. The idea being that these are what are important for developing the toolchain. It's an open standard, which we think is quite important. You can obtain it for free from the internet, from the OMG's website. And there are actually, apart from OpenRTM, our OpenRTM, there are also many other implementations of the standard already. There's OpenRTM.net, Opros, which is the Korean national middleware, Ghostai RTC from France, and several other ones for example, CANopen and embedded systems. Not all of these are unfortunately open source. For example, OpenRTM.net is not open source, but several of them are. OpenRTM and Opros, most importantly, are open source. So another part of the platform is the tools that go around it. Without tools for your middleware is very hard to use, and it's not really a platform at all. So the RT-Middleware project includes numerous tools, many of which are open source. Today I'm going to talk about several of the tools that are developed at AIST. Not all of them, but several of them. And the ones I'll talk about are all open source tools. They're all freely available. One thing we do with a lot of our tools, particularly the GUI tools, is we try to integrate them into Eclipse as plugins. This is so we can create a complete IDE where you can step through the process of developing a robot system within one IDE just by changing perspective. So RTC Builder is our graphical tool for designing RT component specifications. Using this tool, you design the port layouts, the metadata, configuration parameters, and so on of your component. And this is saved as an RT profile specification, which you can then use to generate template codes in any language of your choice that we support, which is currently 5 languages, I think: C++, Python, Ruby, Java, and .NET. And so the idea is that because you have the specification, you can generate template code again and again and create different implementations of the same external interface, allowing interchangeability. To complement this, we have RT System Editor. So while RTC Builder is for making components, RT System Editor is making for entire systems. So you use this to combine components together, linking their ports and setting their parameters, and you can then save that out as a system which can then be deployed onto your robot. It's also capable of interacting with running systems, so you can use it as an introspection tool. This panel on the right here shows all the properties taken from this component here, which is actually running at the same time. So it's all real-time introspection, very useful for debugging and system inspection. We provide a command line equivalent to the graphical tools called RT Shell. We use this in resource-constrained environments, and also when we want to automate stuff, like for example automating the deployment of a system. We can use RT Shell for this because we can script it with, for example, bash script or batch files. It also performs some functions that are not available in RT System Editor. Along with these we have libraries, because sometimes a tool is not enough. Sometimes you actually need to have a lot more flexibility, and that's where the libraries come in. So a couple of the libraries we provide: RTC Tree is used as a Python library for interacting with components at runtime, and RTS Profile gives you an execution time model of an RT system, which you can then interact with and use to introspect and for example, save for deployment later on. We've recently also started a project site on openrtm.org where we allow other people to upload their components, to register their components and tools and so on. In the 2 months or so since that went online, we've seen over 100 components, component groups and tools registered. I'm sure Rosin will recognize this one in the middle here. This is our Open Rave component. We also have components for simulators, for robot hardware, for algorithms such as maps and localization and so on. So a bit of a summary. So RT-Middleware is developing a complete platform for robot development, and large parts of it are open source and freely available. Everything that AIST does is available as open source. We have several tools to go with our middleware, and everything's available at openrtm.org, and I invite you to go to the website and check it out. There's also a YouTube channel where we have demo videos and instructional videos and so on. Okay, thank you.